All right, gentlemen, it's over to you. Jim, you want to take it, or Mel? Either one.
Okay, I guess I have it first, and you might want everybody mute except Jim. And then if you have any questions, just unmute and jump in, and I will answer the questions on the spot. The idea is that I wanted to bring people up to speed on terms of the technology that we have used and are currently using in tracking the balloon. So I get questions on that, like how are you able to get the balloon when it's over Greenland and all. So I'm going to, if I find my thing that I want to find here, here, and look at the technology behind high altitude balloon tracking. There we go. Now, I've had a license for 63 years, so I can remember way back, and it was probably in the early 1980s that the FCC first authorized digital transmissions. Before that, it was illegal to transmit anything digital with the exception of RIDI. So when the FCC finally allowed digital transmissions, the first thing that came up, or one of the first things that came up, was called AX25. And X25 was established format, but AX25 was a slight modification that allowed us to put our call signs in and make things legal. And the way it worked was that everybody's on the same frequency, and suppose I want to talk to Jim, I could send a connect request to him, and this is now done on 2 meters. And initially, everybody's hearing everything that's on the channel. And if Jim accepts a connect request, then there's a software connect between the two of us, and the two of us can chat back and forth. And the format is such that there's a checksum, so that in the background, I'm sending packets to Jim. Jim's computer is comparing a checksum and sending back an acknowledge, and they're going back and forth that way. And that's the way that initially we had our two-way conversation. But of course, we're on 2 meters, and since we're on 2 meters, we're limited to very short distances. So the next thing that came up then was a repeater. So let's suppose that maybe somebody with the call of an 8 NOQ decides he's going to be a repeater. And since it's a digital repeater, we call it a digipeater. And one of the other things you could do with AX25 was put a second station ID on, because you might have a station in your car and one at home and maybe a portable. So you could use WMV-1-2, and initially you could have up to 16 different second station IDs, but now it's pretty much to the point where it's sort of unlimited. So I could say connect N8P. I could connect N8PCL by way of N8 NOQ-2, and at my station and N8 NOQ then would be sending packets back and forth and acknowledging them, and then N8 NOQ would send packets back and forth to Jim and acknowledge them, and that's the way it would communicate. Initially, it was set up so that you could string up to 7 repeaters together, but that never really worked, and 1 or 2 seemed to be about the maximum. So that would have gone, X25 would have gone the way of AMTOR and PACTOR and some of the other modes if it had not been for a man by the name of Bob Berninga, WB4APR, who's on the staff at the Naval Academy at Annapolis. One big event at the Naval Academy was the Army-Navy football game. And they had established a procedure that if the game was to be played at West Point, the midshipmen at the Naval Academy would establish a relay and would carry a football in relay from Annapolis, Maryland to West Point, New York. So Bob got the idea it would be really neat to use ham radio to follow the progress of this football as it went from Annapolis to West Point. So he designed a system, and at this point, GPS receivers now are just coming into play. So Bob Berninga designs a system where he takes some of the data from a GPS receiver, puts it into the message packet of an AX25, transmits it, and then he designs the software with mapping to follow the progress of the football. And this worked, and it was the first transmission of APRS, Advanced Packet Receiving System, which not and uncoincidentally goes along with this called WB4APR. So after this happened, then of course a lot of people picked it up and say, hey, that's really neat, I'm going to get me one of those APRS setups. And APRS then came into being, and that's the only vestige of AX25 today. But it was limited, of course, because it only worked locally, and you could set up 1 or 2 digipeaters, but you couldn't do any more than that. So the next person we meet is Tapio Sakura, OH2KKU in Finland. And of course, at this point now, we start to integrate the internet along with ham radio. So Tapio Sakura said, here's what I'm going to do. I'm going to set up an internet site called APRS.fi. And anybody who wants to can send me the information from APRS from your locality. I'll incorporate all this into one website, and then you can get on the internet and you can see what's going on anywhere. So we established then iGates, or a gate is a device that will transfer information from one network to another, and then iGate then translates it from the internet. So now we have APRS activity going on pretty much all over the world. It may have to go through a digi, but when it gets to an iGate, it gets on the internet. That gets picked up in Finland. APRS.fi then transmits the signal on the internet for anybody to see. And now, at this point now, we have something that's usable for a balloon, because now the balloon, as long as it's picked up by an iGate, will get onto the internet. And in 2018, when we launched W8MV-11, this was the format that we used. And it worked great as long as the balloon was over Europe or North America. But once you get away from Europe and North America, the number of iGates gets very small. In fact, I think we set a record for the longest time that a balloon has ever been unobserved and then came back. It was on its 5th time around the world in November, and we stopped receiving any signals. So our goal was just to get around the world once, so we were happy we had a successful launch, and we put it to bed. And then in February, I got email from these guys out in California who manufacture the balloon. They said, hey, Mel, your balloon's back. And we looked, and it was over Saskatchewan, and it had been totally quiet for 3 months. And we assumed what had happened is that it headed north. And when you get near the North Pole in the winter, 3 things happen. 1, it's cold. 2, it's dark. And 3, there aren't any iGates. So apparently it just meandered around the North Pole for about 3 months. All of a sudden worked its way back down into Saskatchewan. And then it started transmitting again and transmitted until the following May, I think was the last we heard from it. And we assumed that it had been around the world about 17 times. So this was the technology that we used then for W8MV-11. But we still have a problem because you've got to be in range of an iGate before you get on the internet. So the next person we encounter then is Joe Taylor, K1JT, has a PhD from Harvard, and he's a Nobel laureate for discovering a new type of pulsar. But in ham radio, his interest was in weak signal propagation. So among other things, he developed a system called WSPR for weak signal propagation reporting. And the idea there was that people would transmit very low power and be received by other signals around the world and put on the internet. So let's suppose that you want to get on the air, but you don't know what bands are open. And you could turn on your radio and tune around and see what it sounds like. Or you could go to the website, whispernet.org, select a band anywhere from 20 to 10 meters, put in my call and update, and it will show you all of the signals that are, all of the stations that are receiving my signal, because I broadcast at 250 milliwatts, that's a quarter of a watt, into an R5 antenna, first on 10, then 12, then 15, then 17, then 20 meters, and it cycles 24/7. So if we look at this particular time on 20 meters, you can see that all of these stations here have received my signal, and there's probably 100 of them, some as far away as Australia. even though I'm only transmitting 1/4 of a watt into a vertical. So then at this point you say, well, so what? Whisper is not designed to track a moving object. It's designed to report signal strength of a stationary transmitter at different points. So is there then a way that we could use Whisper to track a balloon? Because now we're on 20 meters, and if we're on 20 meters, we don't have to worry about being in range of an eye gate. So Joe Taylor's Whisper specifications are shown here. So it transmits 110.6 seconds of a continuous wave. And in that 110.6 seconds, it's shifting to one of 4 different tones every 0.683 seconds. And the tones are separated by 1.46 hertz. That gives us a total bandwidth of only 6 hertz. But we're only transmitting at 1.4648 baud. Now, thinking about why this works, because noise is proportional to bandwidth. So if you can get the bandwidth very small, then your effective gain is very high. It's like a signal, it's like a gain bandwidth product, where the more narrow the bandwidth, the higher the equivalent gain. But of course, the baud rate is very low. And as a result, it takes 110 seconds to transmit 12 characters, 6 characters for the call sign, four characters for 4-character grid square, and 2 characters for the power and dBm. So then the question was, how can we use Whisper to track a moving object and use it for a balloon? So at this point, then the next person we encounter is Bill Brown, WBAELK. And he says, how are we going to transmit the altitude, system temperature, system voltage, 6-character grid square on a Whisper packet? Answer is, you can't do it. It's impossible. So then he said, well, what about 2 transmissions? And he then encoded 2 subsequent Whisper transmissions. So it takes a total of 4 minutes. And with those 2 transmissions, we can now get the data that we want. He and a few other people pick up these 2 transmissions and form a Whisper, and form an APRS packet. And they add a SSID to it and form an APRS packet. So as far as APRS.FI is concerned, this is a signal that has been received over the air on 2 meters. But in fact, it's a signal that has been created by Bill Brown to make it look like an APRS signal, forwarded to APRS.FI, and at that point we can get on the internet and track the balloon. That's what I wanted to show anybody. If you have any questions, I'm open. If not, we'll turn it over to Jim. Okay, Jim, you want to take it?
Okay, you need to unshare, I guess.
Okay,
Okay.
you got it.
And I'll share a screen, and here we go. Okay, so Mel will talk to you about Whisper and APRS, gave you some details and history associated with that. And what I'm going to do is I'm going to talk about the preparation for the launch and the actual launch date. So let's get on with the show here. Well, the first thing we had to do is we had to purchase the items that were going to be associated with the launch. We got a Sky Tracker kit from Bill Brown, and I ordered that, and it came to my house. And then Mel ordered a balloon from Scientific Balloon Solutions. It's the SBS 13 balloon, and it's approximately 3 feet wide and about 7.5 feet tall. It kind of looks like a dry cleaning bag, okay, but it's much more rugged. I've been told, but I can't really confirm this, that the plastic that's used is the same plastic they use to wrap sushi. So, but anyway, the balloon is made by Scientific Balloon Solutions. On our first successful launch, which was the W8 MV -11 here, they gave us a pre-stretch balloon. We needed to pre-stretch this. They said, we did that once, we're not gonna do it again here. Now, we also had to decide on what was going to be used as the lift gas. And on this balloon launch, we used the same thing as we did on the previous two, which is hydrogen. So it's H2. It's a diatomic atom there, or molecule. And we got the hydrogen gas from Dan Galehouse, who we have lunch with at least once a week, and his call's N8NZZ. Part of the reason why we used hydrogen instead of helium here is that it leaks out of the balloon at a much slower rate. And as a result here, it was a good choice. Hydrogen is much cheaper than helium. And the only drawback is it is flammable. But if you do light hydrogen, balloon with hydrogen in it, it burns at the surface. It burns hot, it burns rapidly, but it's not explosive, so to speak here. So all we had to do is give up our smoking and have no sparks around there. So anyway, we've now decided on what we're going to use for the lift gas. We've got our balloon and we've got our tracker. The tracker kit included the essentially two 5 meter long wires. So we had our dipole vertical antenna also. So we needed to pre-stretch the balloon, because with the pre-stretch balloon that we did a few years ago, we contributed part of our success to the fact that the balloon was pre-stretched. The guys at Scientific Balloon Solution were nice enough to give us a procedure, and essentially what they told us to do is to fill the balloon up to about 0.1 PSI gauge and measure the circumference of the balloon then. So we did that, and Mel then took a string to measure it, and he tied the string off at the 100% point, and then he measured the string and measured out another point that was at 10% higher than that, or at 110% of the original circumference here. And we checked every so often to make sure that we did not exceed a stretch that went beyond 10% of the original circumference. I think our final pre-stretch balloon got to about 7 or 8% above. I believe that's what we found out, Mel. Okay, and so the procedure is you fill it up on the first step. You usually fill it up to the 0.1 psi here, and then after you've done the measurement here, then you go and you pump it up to 0.15. Okay, and at this particular point, you start to hear the balloon stretch. You can hear this creaking and stretching and groaning, like noise coming from the balloon here. Okay, and we let it stay there for a while, and then we went up to, what was it, 0.175, and then it started creaking and groaning quite a bit more. Okay. And of course, whenever you stretch the thing, you pump it up to a given pressure here. And then as the envelope stretches here, the pressure drops in the balloon. Okay, so we would wait until it dropped down to about 0.15 PSI gauge. And then we would pump it back up to 0.175 PSI gauge. And we cycled through that several times there. Then we finally went up to 0.2 PSI gauge, and they told us to keep cycling between 0.2 PSI gauge and 0.17 PSI gauge here until it stopped dropping below 0.175 gauge here. And I think we got it to stay up there for like 10 or 15 minutes here. and we didn't actually see it dropping below 0.125
Actually,
PSI gauge here.
actually, we chickened out. It was we heard this creaking and all, and we didn't want it to break, so we didn't do the full thing, but we got close to it.
Okay. I forgot about that, Mel. So getting closer to our launch date, we actually pre-stretched it late in the fall or early in the winter. I don't remember the exact date here. But we didn't want to launch in the winter time here. And so then we waited until about the end of March or very early April. And we did a ground test here. We actually did it twice here. The first time we were unsuccessful, and it didn't even have the antenna on it, I don't think. Yes, it didn't even have the antenna on there. Okay, so anyway, we took the system up to the balcony on Mel's house. Mel has a 2-story, or actually it's more like 2.5 stories in the back of his house there, or maybe even 3. And so we went out onto the balcony here. Mel had a telescoping fiberglass mast, and we tied our Whisper sky tracker to that. So now it's hanging out there. It's in the sun. It's in its vertical position here. It was dangling about 1 meter, maybe 3 feet off the ground here. And we could see that it was transmitting here, because there's a little LED on the tracker here that blinks a particular pattern. And so we knew that it was actually sending out packets. And so Mel went down into his basement where he has his station, his Whisper station, and he could see the packet. Even though the tracker's only putting out 20 milliwatts here, since it was only several feet between the antenna and Mel's receiving antenna, it was coming in like gangbusters. It was really wide, taking up quite a bit of space on the waterfall there. Later on, Mel discovered that those transmissions, okay, they're putting out 20 milliwatts in the 20 megahertz band here, or the, not 20 megahertz, the 20 meter band. I guess that's a mistake there. I guess I should say 14 megahertz, okay? So in the 20 meter band here, some of these packets were being received in Western France, okay? So we know that we were gonna be, that the system was very, very successful here. We weren't going to have any problems.
We'd taken even more time to cut the antenna. It was a little long, and we measured things precisely, and we cut the quarter wave parts of the antenna, cut about 1 meter off the wire that he gave us to get as good a match as we could. And of course, there's no feed line loss because there's no feed line. The transmitter is sitting right at the middle of the antenna.
Okay, so now it's launch day here, and so what we have to do is we have to figure the neck lift is what some people call it. I like to call it the net lift here, but so what we did is we took and we used a similar procedure last time also. Mel went out and got a 100-gram calibrated weight. And he told you it had a scale that measures to within 2 milligrams here. And so he put the 100-gram weight on there, okay? Well, actually before that, we weighed the tracker and the antenna, and we found out that weighed together only 15.58 grams.
Jim, it's a good point here to realize that we've got a GPS receiver, GPS antenna, printed circuit board, a 4 farad micro cap, a 20 meter transmitter, and a half-wave dipole on 20 meters. And the whole thing weighs 15 grams, which is about half an ounce.
Yeah, it's very impressive. I do know that Bill Brown said he used the thinnest printed circuit board material he could find, okay, to keep the weight down. Our desired neck lift was going to be about 6.5 grams to 7 grams, someplace in that. I think last time we used 7 grams. Mel wanted to go a little lighter, so we went to 6.5 grams this time here. So what we're going to do is we're going to tie the balloon without the tracker, okay, to the 100-gram weight here, okay? And so what we want to do is we want to take the 15.58 and subtract that from 100 grams and the 6.5 grams from the 100 grams here, and you come up with 77.92 grams. So what we're doing is we want the scale to read 77.92 grams. Well, we always have a tendency to overfill, okay? And this may be where some of the other balloonists are getting into trouble. Your tendency is to overfill it, but unlike them, we squeezed hydrogen out. I think we went through 2, 3, 4 cycles of squeezing hydrogen out until we got the thing to read about 77.92 grams here. We were looking for about 78 grams here, but this is what we finally settled at. Okay, so the next thing that we did, and you can see the little picture here, is we had the balloon, and then we fastened the tracker with its antenna onto the weight. But this time, before we tied it on, Mel put the 100-gram weight on the scale, and he then zeroed it out. So that became so what we're trying to do is measure the tare weight here then. Okay, and so as a result then, the scale turned out to read 93.46 grams here. So that meant we're going to have 6.54 grams of lift here, okay? Now, the reason why you want to have such a small lifting weight here is that you want the balloon to go up, and as it goes up, the air density drops, and so the net lift or the neck lift actually drops off here, okay? So at ground here, we were at about what, 0.3 kilometers or something like that. And then as the balloon would rise here, the air is becoming less dense, so the neck lift drops off. So we went to somewhere along the line, it dropped to 4.75, let's say, and then it went higher and it dropped off to 3.25, and then it even went higher and it dropped off to somewhere about 1.75 here. And of course, it's dropping off in a somewhat continuous manner here. And then finally, when you get up to about 10 kilometers, or actually it was 10.3 kilometers here, the lift has dropped to 0 grams here. And so what happens is the balloon floats at that altitude. You call that the float altitude here, okay? So that was our goal here. If you put too much too much lift in there, okay, set it up at like 8 or 10 or something like that, and on our first unsuccessful balloon here, we could only measure in 2-gram increments, and we don't really know whether we were at 8 grams or whether we were at 9 or 9.5. We don't really know anyway. So in that particular situation, the balloon went too high, the float altitude was too high, the pressure was too high on the balloon, and somewhere out over western Pennsylvania then, all of a sudden the altitude started dropping rapidly here. Okay, so here's some actual pictures from the launch here. So here's Mel. He's taken the balloon out of this little shipping tube here. Okay, that he put it back in. This is the pre-stretched balloon here. Okay, we're laying it down on the table. And you'll notice on the table, there's that little red and silver item there. That's his scale. And there's also that little chrome-like looking object here. That's the 100-gram weight here. Now we learned from the first, actually the second launch here, this is the third launch. We learned from the second launch here that if you try to fill it up with a balloon fully extended here, or put gas into it fully extended, it's going to be rubbing up against the ceiling of Mill's garage here. So we folded the balloon in two, and we put some little, a small little piece of painter's tape on there, and that keeps the balloon folded in two. And then Mill added some hydrogen here. We put the regulator on the canister here, and there's a flexible tubing there. And one of the things that come in the kit on the Bill Brown kit is this little white stiff tube that Mel has here, and Bill Brown has rounded it off with heat so that it's not sharp and it's not going to poke a hole in your balloon here. So Mel pushed it up there, and we turned on the regulator, and we guesstimated where we wanted to. And like I said, we overinflated. So we had to go through several steps of pushing the hydrogen out of there, and then reweighing it without the tracker and the antenna on there. So here you can see on one of the cycles here, I'm tying the string on the balloon here to the weight on the scale here, and we went back, and it took us 2 or 3 tries here, maybe 4, but finally we got it to the point where Mel and I and Tom Price there, that's Tom Price in the back there, decided that we were probably pretty close here. Okay, and so here you can see that the balloon is tied to the weight, and Mel's looking at the scale here, and as a result, instead of reading 100 grams, it's reading 100 grams minus whatever the lift of the balloon at this particular point happens to be, and it was around 78 grams at this particular point. Okay, so so finally we got it to the point that we were really interested in taking the neck lift measurement here. So I tied the tracker onto the balloon here, and we've got the antennas coiled up there, and they've got little pieces of tape here to prevent them from unrolling here. And we tied it to the weight. Before we tied it to the weight here, Mel put the weight on the scale and zeroed it, okay? So we're actually doing the tare weight here, and then I tied it on there. And what does it turn out to be here? Okay, oh, excuse me, I'm wrong. At this particular point here, we have 93.48, looks like it, milligrams here. And so if you do the subtraction, that turns out to be about 6.54 grams of lift. Okay, so now it's time to seal off the balloon. And so the people at Scientific Balloon Solutions suggest a particular heat sealer iron. And so we bought one of those for the second balloon launch here. Or maybe we even had it for the first balloon launch. I think we had it for the first balloon launch. Okay. And we set it up here to 400 degrees here. And that's a little parchment paper here that's folded over. And what I'm doing here is I'm going back and forth and sealing the neck of the balloon off. And then I folded the neck of the balloon up, and we tied this string to it. And then I took the parchment paper, and now I'm sealing the folded over flap of the neck of the balloon here to the rest of the balloon here, so that we have confidence that the string is not going to come undone here. Okay, now someplace off screen here, somebody is holding the balloon. Okay, and I think it was Tom. Okay, so Tom's holding, we untied it from the tracker, and Tom's holding the balloon here. And you see in my hand there, I have this little plastic top to one of the plastic trays that we used during the launch here. Mel took the bottom half of the antenna, the quarter wave of the antenna, of the half wave antenna here. He unrolled it here and took any tangles out, if there were any tangles here. And that consists of, you can see here in the next picture, you can see the yellow. The yellow part is a fishing line, and then the red or the copper colored stuff is enameled magnet wire here. And so he got all the kinks and things like that out of there. I walked over and gave him the lid, and he started to wrap the antenna around the lid coming towards me at the table. Then we taped it off, and then we taped even the tracker to the lid here, and then Mel repeated this for the upper half here, and we taped that down also. Then we tied the end of the antenna back to the balloon here, and we let Frank be the crawler for our launch here. So Frank went outside, and you can see him holding the tray there, and and the balloon here, and you can see it's not all that inflated. You know, I had pulled the tape off of here. It kind of looks half inflated. It looks like it's not going to work at all. But anyway, we took it over into Mills' backyard. We pointed it towards the sun there, and we watched the little LED to see that it was doing transmissions here. So we were confident that we hadn't broken in antenna wire. And so then Mel and Frank were inside Mel's basement there at his whisper station there, and we saw the packet go out. And the next thing I know, Frank's sticking his head out and said, "We got it, we got it." Okay, so now it's time to launch the balloon here. Now here's the sequence here. Okay, in the first slot, the LED is off. Okay, and then about 1 minute before the first transmission, the LED comes on. It blinks at approximately a 1 hertz rate here, or one pulse per second here. Okay, and it does that for about a minute here. And then you move on to slot 2, and in slot 2, the SkyTracker is sending the standard whisper packet. So it's sending the call sign, it's sending a 4-digit or a 4-character grid square here, and it's sending power. But the power is actually bogus, and we'll see what it is. The power portion is not truly the power that's being transmitted. Then it goes off for about 5 to 10 seconds, maybe 15. Okay, waiting for the next 2-minute frame here. It was in slot 3 for a full 2 minutes here, and then slot 4 here, the LED comes back on again. Okay, and it sends the phantom packet or the illegal packet or whatever you want to call it, and we'll see how you can decode that. Okay, in the next few slides here. Then it goes off, and so that means now the complete packet has been sent here. And at this particular point, it could be bridged from Whisper to whatchamacallit, to APRS.5. Okay, and so the next thing is in slot 5 is we really go back up to slot 1 and we wait for the next transmission here. We send whisper packets about every 10 minutes here. Okay, it is every 10 minutes here. It appears that Bill Brown only sends the packets to APRS about every 20 minutes here. So he skips a packet every time. It was a still day, and so Bill went out and he backed his pontoon boat out from underneath the cover, and then he pulled up to the dock, and we all, myself, Tom Price, and Frank, got on the boat here. And Frank and I are kind of holding the balloon there a little bit, preventing it from whipping around very much. It was a very still day. You can look at the lake here, and it was like a bathtub, so to speak, here. And so Frank's got the tray there, and I've pulled the tape, some of the tape off here, and he's starting to unwind the tray here, which is allowing the balloon on its antenna tether here to go up in the air here. And so you can see here, I took a picture here when he was just about at the tracker here. And you can see here, I'm helping him take some of the tape off the tracker here. And then he keeps winding it out. Now you can see the balloon, you can see the upper half, the quarter wave of the half wave dipole. And then you can see the center feed, the tracker in the middle, and it's being fed there. Now the two little black objects out to the side are the solar panels here. And now at the last minute here, Frank's holding on here, and I guess we got a little bit of painter's tape that went up. It really didn't need to, but you can also see by Frank's hand, there's a little piece of yellow tape there. I don't know if it's true Captain or not, but anyway, there's a piece of tape there, and about every meter or so I'd say about every foot or so on the antenna there, he's taped the fishing line to the magnetic wire here. Now Frank's let go of it, and it's starting to go up and up, and I think we're at this point, we're starting to head back towards the dock here, and it's getting smaller and smaller. You can't even see the tracker anymore. Okay, and so once we got back to the dock here, Mel then went into the house and sat there and waited for the first packet to come in here. And we received it, and we were successful. And if I remember right, we even decoded it at that particular point, or at least partially decoded it. So and the first packet what you have is your legal call, which in this particular situation is W8VPV. We're using the club call here. And then there's a 4-character grid square. And then where the power is supposed to be in milliwatts, in dBm, in dBm, we actually encode the rough altitude. The altitude to the nearest 1,000 meters is what happens there. Then in the second packet here, where the call sign is, there will be a call sign, an illegal call sign that starts with either a 0, a 1, or a Q. Okay, and there are no legal call signs in the entire world here that start with a 0, a 1, or the Q. And so we use this to do two things: to indicate that this is a balloon's data packet here. That's not the word. Telemetry packet's the word I'm looking for. That this is a balloon telemetry packet here. Then we send the same 4-character grid square that we sent with the first packet, even if we were actually in a different grid square, okay? Or maybe a different 6-character grid square. You're using the 4-character grid square along with the time to indicate that this is the second packet here. And then the power here is a fine adjustment on the altitude here, which gives you it to, is it to the nearest 30 meters? I think it might be the nearest 30 meters, okay, of altitude here. So for instance, here's the timestamp, okay, that would be in the Whisper database here, okay, and you notice that the last 5 are, last 3 characters are 5, 6, 0 here. This, if you're interested, this is in Unix epoch time. So the number of seconds since, what is it, January 1st, Greenwich Mean Time, okay, is 0000. Okay, then you can see EN90 and Mel's house or the lake, I guess is what I should say, is an EN90. And then there's 3, that's the course altitude here. Okay, so we can decode that here. And Bill Brown gave us a nice little spreadsheet that tells you how to decode it here. And it turns out that when the power is 3 dBm here, that corresponds to 1,000 meters here, or about 3,280 feet. The second packet, you'll notice that the second packet associated with our balloon here, the last 4 characters are 680. So this is 120 seconds later here, okay, because the epoch time is not in milliseconds, but is in time here. I mean, in seconds here. And you can notice that the call here, and this is what actually was received by Whisper here, is 1T8JFX, okay, EN90 0, okay. So we can see here that you can use a combination of the timestamp, okay, the original timestamp plus 120 here, which would be 16209994,680, and the EN90. Those 2 items then enable us to identify that this is our phantom call, and this has encoded data here. Okay, so it turns out that the 0, 1, or Q here, it does a rough a calculation on which channel it's going to use, anywhere from channel 0 to channel 29 here. So 1 means that it's in the range of 20 to 29 here, okay? Then the T has encoded into it the temperature and the number of satellites, okay? And this it's a rough estimate of the number of satellites here. And it turns out T means that the temperature is 15 degrees centigrade here, and that there are greater than 8 satellites here. And if you look over here on these 2, if you look over here, let's see here, what do I have to do here? Mouse pointer, pen. Oh, there we go. So if you look over here, and let's do the laser pointer. Oh, can we? Oh, I don't see one for this. Okay. So if you look over here, okay, we can see here we can see RST, okay, so this is either an R, an S, or a T here, and if it's a 0, 1, or Q here, okay, yeah, it's a 0 Q or 1, I believe it is, but the T then is the T is in the 3rd position there. That's what it is. The T is in the 3rd position here, and so that means then that there are greater than 8 satellites here, and the temperature is 15 degrees centigrade here. Okay, and then from from some additional information here, okay, we can see the 3rd character here, the 8 here, then tells us then that it's channel 8. So it's 20 to 29, so it's actually channel 28 here. So all you have to do is add the 20 and the 8 here, and you know what channel it's broadcasting on here, or transmitting on. The next thing that you have here is the J, okay, and the J corresponds to what Bill Brown calls the solar reading here. And what this really means is the microcontroller sees 4.2 volts, okay, and so you can tell what its health is and how much sun it's getting at that particular point. And then the easiest thing is the last 2 characters here are the 5th and the 6th character in a 6-character grid square. So if you take your course grid square, which is EN90, and you put the FX on here, then you get the approximate location of the balloon here. What am I doing here? Oh, and so then for the like I said, the power here, it gives you the actually gives you the fine altitude here. What did I have on the previous one here? Oh, that's right. This was encoded in the the T here. So anyway, here to get the fine power is 0, came through as 0 dBm. So that means that the correction on the fine altitude is actually 0 meters here. So the balloon was at approximately 3 kilometers at that particular, yeah, that's right, 3 kilometers high at the point where we got our first reading here. Okay. Bill Brown set it up so that it does not send out packets until it gets to a certain altitude here. Okay, normally. Okay, so you take the fine and the coarse and you add those together and you find out then that it's at 1,000 meters here, which is 3,280 feet. Mel's house is at about 900 feet here, and so you can see it's quite a it's about 2,000 plus feet above the ground level here. And so this little chart here then tells you how you can use the fine reading here to translate that to the altitude steps here. And then I think I had a picture on the previous. I guess I didn't. I forgot to put that in here. I'll add that before I send these off to Anthony. But we have a chart that it'll tell you the rough altitude also. Now I do have some programs I'm working on here that allow you to decode these particular packets here. And for instance, when I sent those two in here, it tells you what the call sign is. It tells you what the grid square is. It translates the grid squares to a latitude and longitude here. It also shows you the voltage, the temperature, how many satellites we're using, the approximate altitude here, and the channel number here. I'm also working on a program that will take this big block of data that you can download, which contains up to a month of whisper data here, to go through and to extract these two packets here so that it can be decoded. Okay, so here's where EN90FX is. This little box rounds that. You see the little arrow here on the East Reservoir. That's approximately where we launched the balloon here. And the little diamond here is the center of that square here. Okay, so the balloon is someplace within this particular box here. If I remember it, it went south first, and then it went back north again, and then it finally started out across Pennsylvania. By the time the balloon really started heading out east here, the whole launch team was down at Woody's eating breakfast here. We got up and we showed up at Mill's place, I think at 6 in the morning, and we were able to launch about 8 in the morning. Okay, so I want to thank you for your attention here. Okay, it says here there are more details about the packets in the next presentation. That's not really true, so I'll correct that. And you can go to the balloons webpage here, and probably the easiest way there is to go to CFARC.org, and then there's a link to CFARC-edu.org, the balloons webpage there. Okay, so if there are any questions here about the prep and the launch here, you can ask them now. If there are no questions, then I'm going to thank you for your attention and return it back over to Pat so that he can talk about field day here.
I have a couple of questions.
Sure.
Number one, I followed Mel's balloon there for quite a while off and on. And I know there was an issue with it not showing up for about 3 months. Do you guys think that that's going to happen with this one?
Well, the difference here is that in the first balloon, we were using APRS, which required us to be in range of an eye gate. But with this balloon, since we're transmitting on whisper and it's on 20 meters, we no longer have that limitation. So since we're transmitting on 20 meters, we expect to have, and if so far are seeing uh, transmissions from all over the world. So that's not, should not be a concern.
What do you think the life expectancy of something like this is?
The world record, I think, is about 2 years, and they were launched with two of these SBS-13 balloons. We were close to the record on our first launch with the W8MV-11. That's staying up 8 months. That's actually quite unusual. I'd say a typical launch would be a couple months, but there's so many things that can go wrong. For example, we're at 40,000 feet, and if you get into a major thunderhead, they can go up to 60,000 feet. So there's a lot of things that could bring it down, going over a thunderstorm, and just simply wear on the solar panels was another concern. They were telling us that we should use UV protected solar panels out of California, but the weight of those is something like 3 times more. And you really get a lot of altitude if you use UV protected solar panels. So, you know, we're right now, where we are right now, headed our 3rd trip around the world. It's probably maybe average, and everything after that's gravy.
It's lucky, yeah.
But the other thing that's kind of nice is that the fact that we launched this balloon in May, our previous balloon was launched in August. So, you know, we were launching it at the end of summer and a lot more storms. So launching it in May, as we did this time, we've got several months of hopefully good weather that's less have to bring it down.
Sweet. Anybody else have questions?
I have a question, John Benson, KAHEKG. You're flying the balloon in what's called Class A airspace. I just am curious what steps were taken to prevent collision with aircraft at that altitude.
FAA regulations say that you can fly whatever you want as long as it weighs less than 4 pounds. If that thing were to get sucked into a jet engine, it wouldn't even hiccup. We wouldn't even know it. So
Right.
we're well within specs in the FAA. We have a weight of about half an ounce, and we could go to 4 pounds.
Thank you.
Some balloon launches, they will actually notify their local airport. But we found out that when you notify the nearest airport here, they kind of say, thanks, but we're not interested.
Or they could say, don't do it. In either case, we lose. So we don't worry about that. We just throw it up.
Yeah. We just wouldn't make the presentation if we brought down a plane.
Well, there's a lot of discussion about the legality of this, and I don't think there's any problem with the FCC. I think we're totally legal in everything we're doing. The problem is once it gets out of U.S. airspace and goes into other countries. At that point, we're transmitting with a U.S. call sign in countries like Russia and China where there's no reciprocal agreement. And that gets into a very sticky area. And I think that's one of the reasons that the QST wouldn't publish our article, because they were afraid of the legalities of when we transmit it. There is a system that we call geofencing, where there are 3 countries that specifically prohibit transmissions from balloon. There are the UK and North Korea. What's the other one, Jim? You remember?
Eritrea or someplace like that.
Syria or something. I don't know. Anyway, the software or the firmware in the tracker is so precise that it knows when you're in those areas. And if you ever follow our balloon when it goes over England, for example, you'll see that it actually shuts off when it gets in the vicinity of England and then turns back on after it leaves England, just to satisfy their specific requirements that we don't transmit from balloons. And it does the same thing over North Korea. But outside of that, if it's up there, it's transmitting.
The other thing was when it was an APRS balloon, the previous one, it would actually shift frequencies. So the nearest eye gates would be listening at that particular frequency. APRS is at different frequencies in different countries. And it was smart enough to know that in Europe it's at this frequency, and at Asian this frequency, North America at this frequency. So it would actually change the frequency. The actual transmitter for the whisper balloon here is really just a programmable oscillator. Okay, because the bit rate is so low, all you need to do is what? Change the frequency by a single hertz, okay, to encode the data here, or by a few hertz here. I forget how many different. How many
In
different tones are
in
there?
that same token, Jim was talking about channels, but the overall total whisper channel on any band is 200 hertz, because each whisper channel only requires 6 hertz of bandwidth. So as a result, you only have 33 channels that you can transmit on a 200 hertz bandwidth, and that's why we use 30 channels, and that's why we can decode that with 3 different prefixes of the phony call sign.
Any more questions?
Jim, can you
Oh,
unshare?
Frank here.
Sure, all on share.
Frank here. Just real quick question. How fast did it get, and I seem to remember pretty fast, but how fast did it get up to the 40,000 foot cruising altitude from the time we released it? It struck me it was less than about 6 or 7 hours.
I'm thinking it's around 4 hours. You agree, Jim? Something like that.
Yeah. Let's see here. On
We
the
launched it
previous
about-
launch,
We
we
launched
launched it also at about 8:30, something like that, and about noon it was at full altitude. Of course, I thought it was. I came to lunch and I was disheartened because I thought we had lost that balloon too. And Mel said, "No, it's stabilized. It's at full
Well,
altitude."
the interesting thing is that, as engineers, we're used to data asymptotically approaching a certain level. But that doesn't happen here because the balloon's ascent rate is a function of whether or not the balloon's at full pressure. So as you saw when we launched the balloon, it was only maybe a third full of gas. When it gets up to, say, 35,000 or 38,000 feet, at that point, the balloon is fully inflated. And as it goes higher and higher, there's additional pressure inside the balloon. So the ascent rate is lower and lower. So rather than saying a pure asymptotic approach to float altitude, you say an asymptotic approach until you get to full pressure in the balloon, and then you get another slower asymptotic approach to float level. So it gets more complicated than what you would normally think.
Well, we want to thank you for your attention here, and we want to turn the things back over to the club president, Pat, there.
Yeah, I'm going to get out, so take care, Jim. We'll see you tomorrow for lunch.
Okay, I'll see you tomorrow for lunch. It's going to
Thank
be, whatchamacallit, Luigi's. Okay, Pat, take her away.
Thank you, gentlemen, and thank you for a great presentation here. Mel, hopefully we'll see you over the weekend.
Yeah, I am actually planning to do that. In fact, I talked to Tom Price today, and he's bringing the egg beaters to lunch tomorrow, and I have the stakes to mount them, and I'll bring my satellite antenna to field day and hopefully get a few satellite contacts for you guys, and also work some CW pileups with some luck.
Let's hope so. Come hungry because we're going to have food. We'll have breakfast there.
Okay, I think it might get wet, but we'll do what we can.
Well, 50-50 chance.
Okay, take care, guys.
Thanks,
Bye
Mel. All right, a couple things here.